This video is looking at electrons. How do we look at things? Well, what do your eyes see? Everything that comes into your eyes is visible electromagnetic waves. So if we want to isolate the electron and look at it, we're going to choose the simplest atom. What's the simplest atom? Hydrogen. Hydrogen in a gas form can be put in low pressure quantities inside a glass tube. And this glass tube can have two electrodes attached at either end, and about 5,000 volts will make the gas ionize. Same kind of idea is done in fluorescent tubes that you see in all kinds of office lighting. So the same kind of ionization that goes on in this hydrogen gas, or we looking at ionized hydrogen electrons, well, how are we looking at the electrons? The only way that we can see something, the only way that you can get electromagnetic waves is when an electron loses energy. The more energy the electron loses, the greater the energy that's emitted. This image demonstrates the energy level changes inside a hydrogen atom. And what I'm going to do is first start with this section down here, which is ultraviolet light, ultraviolet electromagnetic radiation. This N1 represents the lowest energy level of the hydrogen atom. And since the electrons in the hydrogen gas can only achieve energy levels around the hydrogen nucleus, these are the tight spectral lines that are seen. Not even light distribution, but spectral lines. Not like black body radiation that has distributions of frequencies evenly spaced throughout all of these. There's only discrete ones that can occur. So, notice this one, which is ultraviolet. These are not visible in these other ranges. So let's see what kind of ultraviolet energies we can achieve. As we go from this point to the left, we're achieving higher energies. So let me scroll up a little bit so we can see what's going on. What does n equal infinity mean? This means that you've got an electron which is going from outside the atom. It's not attached to the atom at all, and it's going all the way down to the ground level. Well, there's all kinds of other choices here because we can go from these different energy levels, all the different combinations that exist. But this is the highest energy level that you can see from the electron. So basically, you're looking, when you see this highest energy level, you're looking at an electron remember what I said about looking, you're looking at an electron that's gone all the way to the bottom level there. So these other things follow the same thing. These are the visible ranges. These are infrared, and these are infrared. All of these are spectral lines that come from that hydrogen atom. From other videos, you should have seen this relationship. And this is what Max Planck came up with. His constant times frequency equals the energy. And when it was plugged into the distribution thing, it exactly matched up with the black body relationship. But here we're just talking about a single atom. We're just talking about the single atom hydrogen. So really, what are we looking at? Are we looking at total energy, or are we looking at the difference in energies? If you notice on that last diagram, we talked about difference in energy levels. So let's talk about it this way. Let's talk about it En2 minus En1. Remember that the only time you get a photon is when an electron changes energy level. So we're not looking directly at the electron energy level. We're looking at a change in those two. So if that's true, then let's say that would be HF1. I'm sorry, that would be 2 minus HF1. That's when it's changing from a second energy level to a first energy level. This would be one of the spectral lines that was the ultraviolet. So how do we relate to that? Well, we can relate to that and call it H times F2 minus F1. These are difference in frequencies that occur. Before I go on, let's look at this. N2 would be a higher energy than N1. So if we take the higher frequency minus the lower frequency, this will be the difference in energy, or the energy that represents the energy that the electron lost, and that's going to be the frequency of the radiated photon. Now, why do we limit it to these frequencies, or how do we know what the limiting factor on these frequencies is? It's over here. It's the energy of the electron over Planck's constant. So these are the discrete energies, the only discrete energies that can exist. And these are the only discrete frequencies that can exist in this example of the hydrogen atom. What I'm starting here is a hydrogen frequency matrix that lists all the different possibilities. Here's one possibility, is that your energy level went from 1 to 1. Well, that's not going to be any change at all, so no photons are going to be. And then if you go from 2 to 1, that's going to be 2 minus 1, and that's going to give you a photon in the, that's one of the lines that was shown for the ultraviolet. Then energy level 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1. That they actually keep going here, but I'm just going to stop at 7 because that's what was shown for the hydrogen atom. Once you get above 7, then the electron is no longer attached to the atom, and it just becomes a positive proton all by itself. So all of these are going to emit a photon. But what about these? If you take 1 minus 2, in other words, you're going up in energy, then that would if this number is smaller than this number, that means you're actually going to be absorbing a photon. You absorb a photon, and then the energy level of the electron goes up. So let me fill in a few more of these pieces, and so you can kind of get the idea. Okay, notice we've got, when we start filling these things out, we're going to have a 0 diagonal that goes on this matrix because all of these are 0. Everything below this diagonal are going to represent photons absorbed, so that the energy of the electrons increase. Everything to this side of the diagonal is going to represent photons that are radiated. So it really covers not only the radiated frequencies, but also the absorbed frequencies, the absorbed photon frequencies that change the energy levels. Now let's break this down to a little bit more manageable matrix. Here I've chopped up the matrix just enough so that we can get the first visible spectrum, the spectrum that shows up between energy level 3 and energy level 2. So rather than just put the frequencies, though, we can also derive the frequencies from the relationships that we've already presented, E equals HF. We can also come up with the energy level differences that occur. So we can build a matrix of the energy levels. And also, from those relationships, we can also show a difference in momentum values that occurred. So these matrices can be used to perform uh, physics calculations on the electrons, and essentially, this is what's called matrix mechanics. A lot of times, to learn something, you have to find out what you don't know. And what I find out now is that I don't know how to explain to find the first absolute energy of the electron. All I've been doing so far is talk about how we can use spectral lines to see the difference of energy levels. The energy level drops down one level, and then we get a photon flash of a particular frequency. But that just tells us what the difference in the energies are. How about that ground state energy? How can we possibly explain that one? That's what I don't know, and that's where I have to go next. It's possible I'll delete this video because I don't really make any great conclusions, but at least you're with me as I go through this journey.